So we're going to talk about the different types of printers and filaments. Now, for tonight, we're just going to focus on the extruder type printers. So like I said, this is available online, and a couple of these are articles from a couple of specific websites. Let me zoom in a little bit. So what we're going to be working with are the direct 3D printers, the extruder types. These are the ones like the Prussias over here, the orange and black ones. This big guy here, this MakerBot. It's the extruder type that takes a roll of filament, a plastic spool of filament, and it basically has a hot glue gun on a control mechanism that it forces plastic through. That as it heats up, doesn't melt like liquefy, but it gets warm enough to get pliable, and it squishes it through, and it deposits it in the design of your model. So, like we talked before about with the histories in 3D printing, FDM, fused deposition modeling, is material extrusion. It is pushing material through an extruder, very similar to the project we just finished, through a nozzle, and is joined together with everything. This is essentially the standard. As in, yes, there are other types. There is SLA printing, bless you, with laser printing, with the stereolithogram printing, which is the resin printers, like we discussed in the history of. There is laser sintering, which is usually a powder, like be that plastic or metal or anything like that. That's how it fuses material together. This just heats up plastic filament and squishes it through a nozzle, and that nozzle it gets moved around. Typically, these are polymer based. And there's two major types of filaments. There are so many others, and then subcategories because there are specialty filaments. But we are going to focus on a couple just because it's what we have access to, and it also is the most reliable ones. You can always get into more. Um, it's also one of the most accessible. It's also very shelf stable. Unlike, say, resins, where it cures through I almost said photosynthesis. No, it's not a plant. Through UV exposure, photopolymers, this doesn't cure or change state. It only really gets warmed up, squishes out a little bit, and then gets deposited. That's about it. So as it is, it's pretty much the regular standard. So background wise, stuff we talked about with history of with the RepRap project, these were using traditionally either PLA or often enough they were also using ABS, a different type of plastic that is very strong comparatively, but it takes a much hotter temperature, and where that bonds much better. The problem with that is it's a lot less stable in an open environment like these are without a shroud around them, so they're really prone to distortion. So with this, we're kind of jumping ahead here. We're basically just focusing on these FDM, these extrusion printers with the RepRap ideas. And these are, as you can see, and as we talked about, these are direct evolutions of that project. We've gone over this before, so I'm not really going to focus too much on the RepRap project and all of that. But that's pretty much the gist of where this all comes from. Fused deposition modeling or the FFF type, same diff, like we talked about before. Really, the only real difference is does it or does it not also have a heated bed to deposit material down to? The standard is material gets deposited onto a heated bed because that creates a much stronger bond for your first incredibly important layer, because if your first layer doesn't stick, well, then nothing else is going to stick. But that's the standard, is that now printers across the board, the base also heats up. So that's the main thing. But it's pretty much straightforward. Like I said, functions basically like a hot glue gun. The heating element warms up enough to the not liquid point, but just to the transition temperature point of these polymers, of these plastics. Essentially, it's not liquefying, it's just getting it hot enough to just squish out. Again, kind of like a hot glue gun. It's not fully liquefying it, although hot glue gun does get it really hot, so not a great analogy, but kind of sort of the same. It gets extruded through the filament and it gets deposited down. Makes sense. Obviously, it changes at different speeds, all that kind of thing. One of the main terms, this would be called the hot end. Cool end is a whole different thing. But Ultimately, what these are thermoplastics. It's not a thermoset, it's a thermoplastic. These are plastics that change properties with heat. The difference there, thermoset, is like a liquid plastic that cures solid and rigid with temperature, and you cannot undo that. With these, you could essentially, as long as you don't overcook it or introduce any impurities, you could essentially indefinitely keep reusing these plastics. Be it, make sure you separate them out, they're the same ones, they don't get contaminated, but you could essentially indefinitely keep reheating them, creating new spools of filament out of the chunks, out of failed prints, out of old prints, anything like that, and make new spools and keep reprinting with them. Of course, there's limitations to that, but that's one of the real benefits of the possibilities of these. The hot end is the actual move is the nozzle, and that's what moves around. When it gets to that transition state, that flow state, the material is pushed through and it extrudes outward. I'm not going to go into all that kind of stuff right now, but that's pretty much the main thing. Um, there are some varieties, but one of the things to keep in mind is these get hot. So one of the main things is, if you're not familiar with or you haven't experienced this yet, don't touch the hot thing. Because when I say hot, I mean a lot of these get up into the range of 240 degrees Celsius, not Fahrenheit, so not just above boiling, but like twice as hot. Not quite twice. You do the math. But these can get really hot. So what that means is there's of course a burn hazard. But like most things in life, don't stick your finger in there and you'll be fine. Um, there are some variations in temperature, different materials heat at different temperatures, and we'll get to that in a minute. But we'll talk about those. But that's essentially the thing. But the hot bed does not get nearly that hot because you need the plastic to flow to transition, but not liquefy. Just needs to be warm enough to where it doesn't instantly cool and then delaminate or pop right off. And that's why the bed is hot, but not at nearly at the same temperature. Usually it's roughly, I won't say half, but somewhere around like a third of the temperature. That's not a solid rule. That's just a very rough estimate. Print head motions and all that work differently. Some of them, like you can see up here, the on the two Prussias, the print head moves left and right on those rails, and then moves up. The whole thing moves up and down. Those are the X and Z axes. The Y axis goes left, back, forward, and backwards on these, and that is controlled by the print bed. So any combination works. There's all kinds of different ones. There's also called like delta printers, which is on three axes, where the whole head moves up and down, left and right, or sorry, left, right, up, down. I keep saying up and down. The whole thing moves up and down and all that, and then it move. You could either have the print bed moving or the head moving left, right, forward, and back. So some combination of those movements creates the whole print. There's combinations, like I just said. This one up here, the print head moves up and down, or the print head moves left, right, forward, and back, and the print bed moves up and down. So whatever, it doesn't really matter. Oh, that's what I was talking about. The Delta printers, these Cartesian ones. You can see it's on this triangular method. So through just alterations of that, the whole thing moves around, and either the print head or the print bed moves away from one another. Pretty cool printers. The issue with those is they can be very delicate. The ones like you're seeing up here, this is a pretty standard type now, like your Enders, that sort, with this whole box frame moving up and around. That's pretty much how a lot of them go these days. Um, I'm not going to read exactly all of these, but the real difference is just some are more finicky than others. Some of them are a bit more stable. That's really what it comes down to. Why would you choose like a Delta printer over these? Well, their range of motion is larger, potentially faster. And I don't just mean like the print bed, but the overall print volume. So not just how far it can move left, right, left, right, forward, and back, but also how tall it can get. Because the issue with like these cube style ones here, like the Prussias over here, it has to uniformly get larger. The entire apparatus has to get larger because of that frame, and that vertical frame can get a little floppy if it doesn't. But there's like anything, there's going to be pros and cons with anything. So that's pretty much a rundown of like how these work. Pros, scalability is one of the, like I said, scalability is an issue. Resin printers, you have to have a vat of liquid resin. We're not going to worry about that right now. The FDM printers can get as big as you need, really, and I mean like as big. In your research for the points in history, things like that, some of you may have come across things like being able to print boats, like literal boats, not just like a little toy boat, but I mean like an actual boat hull or a car body, things like that. Upwards of that's even potentially scalable. It's not the exact same thing, but if you've even come across like how architectural printing is happening now with printing with concrete and actually printing houses or bridges or structures like that, it's a scalable function. Those are not the exact same printers, but these basic types are. It's scalable, pretty low cost materials because it's not overly specialized tools. It's just the same things larger. Um, and that's one of the other things that's really beneficial about filament printing in general. The printing material is comparatively cheap. A spool of filament, unless you're getting into like specialty ones that like nylons with carbon fiber and yada 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 in it, they usually run about $20 a spool. And that will actually print you quite a lot. And I don't just mean like, yeah, you'll get a couple things. I mean like you can get a lot out of those. And on top of that, it's shelf stable. As long as you keep it dry, then it'll pretty much just sit there on the shelf. The plastics are susceptible to moisture, but we'll talk about that in a few. Um, Shortcomings, yep, you're limited to like the actual fact that it's not fully fusing. Yes.
There any risk of like dry rot or it getting brittle?
Yep.
Okay.
But the question is, does the filament potentially get brittle or dry rot or something? Yes, only it's kind of the opposite. It's not from it being too dry, it is absorbed moisture, and that actually makes it more brittle.
So there is no risk to it being too dry or
In point of fact, that it's ideally kept dry. In the like, we have these sealable bins that have like the large silica packets. As you'll see when we get over to the makerspace tonight, there are specific dryers that you put it in. It's a dehydrator just for filament, and the whole point is that at a low enough temperature will bake the temperature out. Do not put these in the oven to warm up because the oven gets much hotter than the than the filament stability is, and you will just end up with a oven full of melted plastic. So don't use the oven, just leave it in for a minute. Yeah, when's the last time you totally made coffee or tea or something? And I'll just be right back. It'll still be hot. That was. Oh no. All right, I did make coffee this morning. Same deal. But yeah, so some of the stuff, yeah, shelf stability can be an issue, but as long as you keep it dry, sometimes they're UV, they do get UV susceptible, but honestly, not really. One of the drawbacks can be that like color fastness. I don't know. I 3D printed a license plate holder, say about 6 years ago. And it's held up perfectly fine in New England weather year round. It's not cut in a carport. It's slightly faded from dark black to ever so slightly less black. That's about it. So they're pretty stable. Of course, when we talk about sustainability, that's definitely one of the issues. But oh crud, I forgot to. One moment, please. Okay, all right. So good and strong for the most part. Basically, because it's not fully fusing, it's not liquefying, it is still just kind of like sticking to itself. That's really the downside. And then of course what it comes down to is just how it feeds. Uh, if you don't have the right kind of filament, the right sizing, crap it up, things like that. But the real danger is right there, humidity absorption. Keep stuff dry and you're all set. Print quality can be affected. We'll get into the details of that later, but print quality often enough, you want better prints, keep the filament dry. That really often enough is that's the key. Keep the stuff dry and you're really pretty good. Weird things happen when the filament gets old, and by old usually just means that it has in fact absorbed moisture. It gets weird and stringy, maybe it doesn't stick well enough, things like that. Of course, there are newer filaments that it intentionally, while it's not intentionally left to get moisture, there are some filaments that are intentionally formulated now to kind of work with that and actually kind of turn a little bit foamy. So that's even a thing now. But really, when it comes down to print quality, things like that, as long as your material is dry, couple little bit of calibrations and slicer setting adjustments, and you're away you go. They're pretty standard, or they're pretty reliable. Print quality cons, like I said, any kind of like possible post processing, which we'll hopefully talk about this semester too. But that means when it comes to like sanding or filing, anything like that, they're pretty good. You can always sand plastic, you can always sand filament. Hooray for microplastics, but whatever, it is what it is. The print, the printers we're using, filaments we're using, do not really take to chemical smoothing. The one that I was mentioning before, ABS, can be smoothed with acetone, with solvent. These, not really. But we can talk about that. There are, there's different nozzle sizes, but for the most part, the standard is 4 millimeter or 0.4 millimeter nozzle. That's what these use. That's what this one uses. That's what all the ones in the print in the makerspace use. So that's pretty well standard. So I did want to quickly talk about some of the materials. And while this article goes over them, I prefer the other article, so I'm going to hop over there for a moment. But essentially, the printer options are what we have. So there's different varieties, but for the standard is pretty much, they all pretty much look like that. The Prusas, the Enders, the Crealities, all of that, they're all pretty much those gantry style ones. So real quick, I wanted to jump over to this article just to quickly review what we're going to be working with. Now, we are going to focus on PLA, which was one of the two main ones. But the main things we want to talk about, the two main filaments we're going to be using this semester are PETG and PLA filament. Mainly because these are these are probably the most popular, most prominent, and easiest to use. There's of course a wide variety of other ones you can use. It's up to you. But for what we have access to this semester for our class stuffs, it's PETG and PLA. So what are these? PLA is a very common one used. It's called polylactic acid. It is an organic polymer, and it is created by fermenting things like corn, things like that, and then polymerizing those fermented proteins. So one other thing is, so things like I said, corn, sugar, any of that stuff, it's polymerized and that is able to be extruded into a spool. So works really well. It is a plastic in that it is a polymer. It's not a true plastic, not a petroleum product, but it works very similar. It has a low melting point and a low glass transition point. The glass transition is just when it kind of melts a little bit. There you go. It's not super sensitive to the environment, so these open frame ones, it prints very well where it's not necessary to have like a sealed container in. That works well. Because of its lower melting temperature, it doesn't bond as strong. So PLA is very much one of the like prototyping ones. It's great for like toys, example models. It can work well for like cosplaying, stuff like that. It's just not as strong, but it is available in a very wide range of colors. So it's very common and it's also pretty cheap. It's pretty color fast. It doesn't really, it says UV rays are known to discolor. I personally haven't found it to be that much, but probably on your more extreme colors, reds always, doesn't matter what material it is, reds always fade first. Your brighter colors, it'll probably fade a little bit, stuff like that. The other one is PETG. It's a semi-clear plastic. It is derived from polyethyl tetraphthalate with a glycol modifier. And no, that's not on a quiz, so don't worry about it. Main thing is just so you can remember the acronyms, PLA and PETG, and you're good. That's really all you need to know. It is a modified version of PET, which is essentially everybody that's got a plastic water bottle, that one, that one, that one, that's all PETG. Or sorry, that's all PET. You look at the you look at the recycle symbol on the bottom, it's going to say PET. The only difference is it has this glycol modifier, which helps to lower the melting point of the standard polyethylene tetraphthalate. It just makes it to melt a little bit lower. Now, the problem with that is, and we're going to talk later on when it comes to sustainability, those two can't mix because in a standard recycling center, plastic bottles, regular PETG, sorry, I keep doing that, PET, perfectly recyclable in there. You mix in that glycol modifier, it screws the whole works. And I don't mean like just one little bit of printer filament into the whole batch of bottles is going to contaminate the whole thing. But when you're doing it with an absolute regulated industry standard, kind of, sort of. But that's one of the main issues with it, and that's really the only difference with those. It is a true polymer, as in it comes from crude oils, petroleum based. Um, and then, of course, it has different chemicals in there to modify it to make it better for printing, things like that. Like I just said, many recycling centers will accept PET, but not PETG because you cannot mix those unless it is a specialty recycling center. Oops, what did I just click? I don't know what I just clicked. Anyway, doesn't matter. It's known for being very durable and definitely stronger because because it's petroleum based and it has a higher melting temperature. So the layers will bond together better. Again, it's still not fusing layers, but it does have a stronger bond. That license plate holder I was telling you about, it was printed in PETG. So 6 years on and outside year round, pretty darn good. No durability issues or anything like that. It is slightly more flexible depending on the print or depending on the design. Um, but ultimately, honestly, I have found that, and as the options have gotten better, PETG, sorry, I keep stopping myself, and PLA are essentially interchangeable in their qualities. The only reason you might want to choose one over the other, sometimes there are more colors available in PETG or PLA, depends on the maker, things like that. But some printers cannot handle the slightly higher temperatures. Like this printer here, this MakerBot, cannot print anything other than PLA, although that's by design. So that's really the only differences. Some are stronger, some are a little more flexible, some are more color fast. The temperature changes, that sort. The main thing is make sure you know which one you're using when you go to set stuff up, because also they cannot mix. It'll as in like the printers will not work the same with the two. We'll go over the other stuff later, but like I said, PETG melts a little bit hotter than PLA. That's pretty much it. It's a little bit stronger. It is a bit more prone to stringing, which is just this, where when the printer goes between things, little bits of string. You know, like when you're using a hot glue gun and you go to pick it up and move to the other thing, that little string,
It's like
basically the same thing.
my friend has a 3D printer and he's giving me like a 3D printed train shelf.
Yeah.
I'll have them with me there.
That's okay.
I can bring
But
one next week to show you.
Okay, sounds good. But yeah, that's pretty much the only difference. They've gotten to the point to where they're all but interchangeable. Mechanical properties, PLA is a little bit weaker because it's a little bit stiffer. PETG because it's true polymer, a little bit more flexible. That's it. Some of them are food safe, technically, but the main thing is it's not so much the plastic isn't food safe. The problem is a print isn't exactly smooth. It basically makes layers of squished up stuff. And just like broccoli in your teeth, little schmutz gets stuck in the little folds. And that's what makes it not food safe. They're harder to clean. Also, do not put 3D printed foodstuffs in the dishwasher. That does get hot enough to warp them also. Ask me how I know. Yeah, I've warped the shit out of them.
Just the food stuff? There. Can
What?
we put like regular?
What do you mean?
You said don't put the 3D printed food stuff. I'm saying, can we put other 3D printed objects in the dishwasher?
The food stuff meaning if you're thinking, oh, it'll clean off the food stuff off of my 3D printed object. It's more that the water gets hot enough to warp the prints. So yeah, that's what I mean. Don't put 3D printed stuff at all in the dishwasher. There you go. So yeah, if you just wash by hand, yeah, it's not going to get hot enough. But most dishwashers kick the temperature up big time with a heater element in there. So yeah, whatever. Learning experience. I'm not going to read all of this individually. This pretty much just goes over exactly what I talked about, and some of this information is outdated as far as color stuffs. But there's a variety of makers. There's a variety for any of the filaments. There's a variety of different types, and there's tweaks we can do to get the most out of those, and hopefully we'll get to some of that this semester. But the rest of this article just goes over some different places to buy from, things like that. I personally found not that much difference between the bulk, but I am generally buying like standard filaments. When you get into specialty ones, that's a whole nother ballpark, and that's a whole nother lecture. So we're gonna end it with that. Just know that pretty much just be aware of what you're buying and what you're using when it comes to your printing, because when you're preparing your prints, that is extremely important.